Welcome to DAR Tutors. Today, we're going to explore a powerful mathematical tool called Markov chains, which is a key topic in IB mathematics. Applications and interpretation higher level. We'll begin by defining what a Markov chain is, which is a specific type of stochastic model. First, let's understand the term stochastic. It comes from the Greek word stochastikos, meaning acting based on guesswork. This refers to models that include randomness or probability. So, a stochastic model uses probability to predict future outcomes. Unlike the exact function-based models we've seen before, stochastic models acknowledge the inherent variation in real-world systems. A Markov chain is a particular type of stochastic model. By the end of this scene, you will be able to define what a Markov chain is. A Markov chain is a stochastic model that describes a sequence of random events evolving over time. It has three core characteristics. First, time is measured in discrete steps, like days, weeks, or years. It's not continuous. Second, the possible outcomes at each time step are called states. These states are the different conditions or positions the system can be in. And third, and most importantly, is the Markov or memoryless property. This property states that the probability of moving to a future state depends only on the current state, not on any of the states that came before it. In other words, the past history of the chain is irrelevant once the current state is known. Let's consider a classic example. Weather. Suppose time is measured in days, and the weather can be in one of two states, sunny or rainy. In this Markov chain, time is discrete, states are sunny or rainy, and critically, the probability of tomorrow's weather depends only on today's weather, not on the entire week's forecast. To recap, we've defined a Markov chain as a stochastic model that evolves in discrete steps between discrete states and has the memoryless property. This forms the foundation for our analysis in the next scenes. Now that we understand the basic concept of a Markov chain, let's explore how we can visualize and represent it. Our learning objective is to be able to construct and interpret transition diagrams. We'll use a visual representation called a transition diagram. Think of it as a map that shows all possible moves or transitions within our system. Let's stick with our weather example. Suppose we have the following probabilities for how the weather changes from one day to the next. We can see that if it's sunny today, there's an 80% chance it's sunny tomorrow and a 20% chance it's rainy. If it's rainy today, there's a 60% chance it's sunny tomorrow and a 40% chance it's rainy again. To draw the diagram, we follow a simple set of rules. First, we represent each state with a node, which we'll draw as a circle. So we have a circle for sunny and one for rainy. Second, we use arrows to show movement between these states. Since we can go from sunny to rainy and from rainy to sunny, we'll draw arrows in both directions. And third, we label each arrow with the corresponding transition probability. For example, the arrow from sunny to rainy gets labeled 0.2. Crucially, notice that we can also stay in the same state. An arrow looping back from sunny to sunny represents the 80% chance of staying sunny, labeled 0.8. We can check our work. The probabilities leaving any single state must sum to 1. For sunny, we have 0.8 plus 0.2. It's 1. For rainy, we have 0.6 plus 0.4. It's 1. This confirms our diagram is valid. Let's recap. We've learned to visualize the dynamics of a Markov chain using a transition diagram, where circles are states, arrows are transitions, and labels are probabilities. We've also confirmed that the probabilities leaving any state must sum to 1. While transition diagrams are great for visualizing, for calculation and analysis, we'll need a more structured representation. Our objective here is to learn how to construct a transition matrix from a transition diagram. We can organize the transition probabilities into a transition matrix, which we'll call T. This matrix is a fundamental component of every Markov chain. A transition matrix T has a specific structure and rules that are essential to understand. First, the states in the columns represent the current state of the system at time n. The states in the rows represent the next state at time n plus 1. Second, the element Tij in the matrix is the probability of moving from state j to state I. It's crucial to get this order right. The column tells you where you're starting, and the row tells you where you're going. Third, because the system must transition to one of the states, the sum of the probabilities in each column must equal 1. This is a vital property to check. Let's apply this to our weather example. We have two states, sunny and rainy. Let's list them in order. To be consistent, we'll define one as sunny and two as rainy. This order is arbitrary but must be maintained consistently. So, our matrix T will be a 2 by 2 matrix with columns and rows labeled sunny and rainy. Let's fill it in. The first column corresponds to the current state being sunny. The probability of staying sunny, row 1, is 0.8. The probability of moving to rainy, row 2, is 0.2. The second column corresponds to the current state being rainy. The probability of moving to sunny, row 1, is 0.6. The probability of staying rainy, row 2, is 0.4. Let's verify the column sums. Column 1, 0.8 plus 0.2, it's 1. Column 2, 0.6 plus 0.4 equals 1. The matrix is correct. To recap, we've learned to build a transition matrix T from a diagram or a set of probabilities. We label columns as from and rows as to, and always check that each column sum is 1. This matrix T is the core of our algebraic model. We have our transition matrix T, but what does it act on? Our objective in this scene is to learn about the state matrix, which describes the distribution of the system at any given time. We represent the state of the system at time step n using a column matrix called the state matrix, denoted as S sub n. The state matrix can represent two main things. It can show the probability that the system is in each state. For example, if we have two states, state 1 and state 2, S sub n will have two entries, P1 and P2, where P1 is the probability of being in state 1, and P2 is the probability of being in state 2. Since these are probabilities, they must add up to 1. Alternatively, it can show the number of items or individuals in each state. If our states are fully fit and injured, SE sub n might tell us the number of players who are fully fit and the number who are injured. In this case, the elements of S sub n would sum to the total population being considered. The first state matrix we usually work with is the initial state matrix, S sub 0, which describes the state of the system at the very beginning. Let's use our weather example. Suppose we know for a fact that it is sunny today. This is our starting point. Since sunny is our first state, its probability is 1 or 100 sa. Since it can't be rainy, the probability of rainy is 0. We write this as the column matrix S sub 0, with 1 in the first row for sunny and 0 in the second row for rainy. Now, let's consider a population example. Suppose a company has 1,000 employees. 600 work in Office A and 400 work in Office B. We want to represent the distribution of these employees. We'll define State 1 as Office A and State 2 as Office B. The initial state matrix S sub 0 would be the column matrix, 600, 400. The elements sum to 1,000, the total number of employees as expected. To summarize, the state matrix S sub n is a column matrix that captures the distribution of probabilities or population in the system's states at time n. Understanding it is crucial for our next step, predicting the future. We now have the two main ingredients of our model, the transition matrix T and the initial state matrix S sub 0. The most exciting part is using them to predict how the system will evolve. Our goal is to calculate the state of the system at any future time step. Let's return to the weather. Suppose it is sunny today, so S sub 0 is the vector 1, 0, 0. We have our transition matrix T. What is the probability that it's sunny or rainy tomorrow? This is the state matrix for the next time step, sub 1. We find it by a simple matrix multiplication. We calculate the next state, S sub 1, by multiplying the transition matrix T by the current state matrix S sub 0. Let's perform the calculation. The product of T and S sub 0 is the column matrix, 0.8, 0.2. This matrix, S sub 1, tells us the state of the system tomorrow. The interpretation is clear. There is an 80% chance it will be sunny tomorrow and a 20% chance it will be rainy. You could confirm this with a simple tree diagram, as your textbook suggests. Now, what about the day after tomorrow? That's time step 2, so we're looking for S sub 2. We apply the same logic. To find C sub 2, we multiply the transition matrix T by the state matrix at the previous step, which is S sub 1. Plugging in the numbers and doing the matrix multiplication, we get S sub 2 equals 0.76, 0.24. This means that 2 days from now, there is a 76% chance of sun and a 24% chance of rain. There's a pattern emerging here. Sub 1 was T times S sub 0. S sub 2 was T times sub 1. We can write S sub 1 as T times sub 0. So S sub 2 is T times S sub 0, which is T squared times S sub 0. This leads to our general formula. The state matrix after n time steps, S sub n, is simply the nth power of the transition matrix, T to the n, multiplied by the initial state matrix, sub 0. This formula is incredibly powerful. We've now learned the general method for predicting the future state of a Markov chain. The state matrix S sub n is obtained by multiplying the initial state S sub 0 by the nth power of the transition matrix T. So far, our Markov chain examples have dealt with transitions between fixed states, like weather or shopping habits. But what if we're modeling a living population that can grow or shrink? Our objective in this scene is to introduce a specific type of matrix for population modeling. To model population dynamics, we use Leslie matrices, named after Patrick Leslie, a Scottish and later Australian mathematician. Unlike transition matrices for Markov chains, the elements of a Leslie matrix are not probabilities, and the columns do not necessarily sum to 1. They are rates of birth and survival. Specifically, the elements describe the rates at which individuals are born into different age groups and the rates at which they survive from one age group to the next. A Leslie matrix L has a characteristic structure. The first row contains the fertility rates, F sub I, for each age group I. These are the average number of female offspring. A female in age group I produces that year. The main diagonal below the fertility row contains the survival rates, S sub I. This is the proportion of females in age group I that survive to the next year, becoming members of age group I plus 1. All other elements are 0. This structure reflects the biological process. Individuals are born into the first age group, survive to the next, or die. The columns still represent the current age groups, and rows represent the next. Let's work through an example with a colony of female penguins, which we'll divide into 2 age groups: chicks, newborns, and adults. We're given that adults lay 4 eggs per year, with a 50% chance of each being female. This means each adult female produces on average 4 times 0.5 equals 2 female chicks. This is the fertility rate F sub 2. We're also told that 80% of chicks die, meaning 20% survive to become adults. So the survival rate S sub 1 for chicks becoming adults is 0.2. Finally, adults have a 60% chance of surviving to the next year, making S sub 2 equal to 0.6. With this information, we can construct the 2x2 Leslie matrix. The fertility rates go in the first row. Chicks are age group 1, so F sub 1 is 0. Chicks can't lay eggs. Adults are age group 2, so F sub 2 is 2. The survival rate S sub 1 goes in row 2, column 1, and S sub 2 goes in row 3, column 2. But since we only have 2 age groups, it's just the survival of adults to stay adults, which isn't part of the standard Leslie matrix structure. Instead, the problem gave the simplified matrix L equals 0, 2, 0.2, 0.6. The problem actually gives the matrix L equals 0, 2, 0.2, 0.6. Let's break down each element. The 0 in the top left is F sub 1. Chicks don't have offspring. The 2 in the top right is F sub 2. Each adult produces 2 chicks. The 0.2 in the bottom left is S sub 1. 20% of chicks survive to become adults. And the 0.6 in the bottom right is S sub 2. 60% of adults survive to remain adults. This simplified structure means the Leslie matrix isn't just modeling survival into a higher age group, but survival within the highest age group as well. Now, let's use it. If our initial state S sub 0 is 250 chicks and 300 adults, we calculate the population 1 year later, S sub 1, by multiplying L by S sub 0. This gives us 100 chicks and 230 adults. By calculating S sub 2 equals L squared S sub 0 and S sub 3 and so on, We can project the population far into the future to see if it grows, shrinks, or stabilizes. This makes Leslie matrices a vital tool for ecologists and wildlife managers. Let's pause our exploration of Leslie matrices for a moment and return to Markov chains. We've seen how a system evolves over time using t to the n times s sub 0. A natural question arises. What happens in the long term? What is the final stable state? This is our objective, to define and find the steady state of a Markov chain. The steady state is a state where the system has reached a long-term equilibrium. It's a point where, if the system is in this state, it will remain in this state for all subsequent time steps. Think about it like this. If you're in the steady state ici nash gasa, then after one transition, you'll still be in the steady state as mathematically, this means that applying the transition matrix T to the steady state vector S gives you the exact same vector S back. This equation, T times S equals S, should look familiar. It's the definition of an eigenvalue problem. It tells us that the steady state vector S is an eigenvector of the transition matrix T. And what is the corresponding eigenvalue? Since T times S equals 1 times S, the eigenvalue is 1. So to find the steady state S, we need to find the eigenvector of T that corresponds to the eigenvalue 1. This is a key connection between matrix algebra and probability. Finding the steady state becomes an exercise in finding eigenvalues and eigenvectors. Let's find the steady state for our weather model. We set up the equation T times S equals S. Let's call our steady state vector S equals AB. This gives us a system of two linear equations. From the first equation, we get A equals 3b. Notice that if we used the second equation, we would get the same relationship. This is because we are solving for a steady state where we only care about the proportion, not the absolute values. This is where the sum to 1 property comes in. Since S is a probability vector, its elements must sum to 1. So A plus B equals 1. Substituting A equals 3b, we get 4b equals 1, so b equals 1/4. Then A equals 3 times 1/4, which is 3/4. So the steady state vector is S equals 3/4 1/4. This means that in the long term, we expect 75% of days to be sunny and 25% to be rainy. This result is independent of the initial state S sub 0. In this scene, we've defined the steady state as a stable distribution, represented by an eigenvector with eigenvalue 1. We also saw that we can approximate this state by calculating t to the n times S sub 0 for a very large n. Both methods are valid and powerful. Let's apply what we've learned to a practical example. This is an exercise from the textbook on BioBlat, a new paper supplier. By the end of this scene, you will be able to construct a transition matrix, interpret its elements, and use it to calculate market share over time. The problem gives us a transition diagram showing customer behavior between BioBlat and its competitors. First, we need to construct the transition matrix T with elements in decimal form. Let's define our states. State 1 is BioBlat, and State 2 is competitors. Our matrix will be 2 by 2, with columns and rows labeled BioBlat and competitors. The first column is from BioBlat. 80% stay with BioBlat. Row 1, call 1, is 0.8, and 20% go to competitors. Row 2, call 1, is 0.2. The second column is from competitors. 10% go to BioBlat. Row 1, call 2, is 0.1, and 90% stay with competitors. Row 2, call 2, is 0.9. So our transition matrix T is 0.8, 0.1, 0.2, 0.9. Let's quickly check the column sums. 0.8 plus 0.2 equals 1, and 0.1 plus 0.9 equals 1. This is correct. Next, we're asked to state the meaning of the elements 0.2 and 0.9. Remember, elements T-I-G mean moving from state J to state I. The element 0.2 is in row 2, column 1. This means the probability of moving from state 1, BioBlat, to state 2, competitors. So 20% of BioBlat customers switch to competitors the next week. The element 0.9 is in row 2, column 2. This is the probability of moving from state 2, competitors, to state 2, competitors. So 90% of customers with competitors stay with them the next week. Now for the calculations. Part C tells us that initially, BioBlat has no market share. This means 0% of customers are with BioBlat and 100% are with competitors. So our initial state vector S sub 0 is 0, 1. We need to calculate T times S sub 0. T times S sub 0 is 1, 9. This is S sub 1, the market share after 1 week. It means 10% of the market has switched to BioBlat, and 90% remains with competitors. Part D asks for BioBlat's market share after 2 and 4 weeks. After 2 weeks, we find S sub 2. We can either calculate T times S sub 1 or T squared times S sub 0. Let's do the latter. T squared is 0.66, 0.17, 0.34, 0.83. Multiplying by S sub 0 gives 0.17, 0.83. So after 2 weeks, BioBlat's share is 17%. After 4 weeks, we need to find S sub 4, which is T to the 4 times S sub 0. Using a calculator, T to the 4 is approximately 0.47, 0.26, 0.53, 0.74. Multiplying by S sub 0 gives 0.26, 0.74. BioBlat's market share is now 26%. We've now worked through a full example, from constructing the model to making predictions. This process of using T to the N times S sub 0 is a fundamental skill for IBAIHL. Hello, we hope you're finding this video helpful. If you're looking for personalized expert tuition in IB, A-Level, or IGCSE curricula, please contact our tutors. Our experienced tutors can provide the support you need to achieve your academic goals. In this final scene, we will tackle 5 IB-style practice questions to consolidate our understanding of Markov chains and Leslie matrices. Our objective is to confidently apply the concepts and techniques we've discussed to solve various problems. First question. The weather in a particular city follows a Markov chain. If it is dry one day, the probability it is dry the next is 0.7. If it is wet one day, the probability it is wet the next is 0.6. Today is dry. What is the probability that it is dry exactly 3 days from now? Let's work through this step by step. First, we need to build the transition matrix T. We'll define state 1 as dry and state 2 as wet. The problem gives us the probabilities of staying dry, 0.7, and staying wet, 0.6. We can deduce the others. Bedrijfsmaatbiom wet is 0.3, and P wet on dry is 0.4. The initial state S sub 0 is 1, 0 since today is dry. We want S sub 3, so we need to calculate T cubed times S sub 0. Using a calculator, T cubed is 0.574, 0.568, 0.426, 0.432. Multiplying by S sub 0 gives us S sub 3 equals 0.574, 0.426. The probability that it is dry exactly 3 days from now is 0.574. Question 2. A country has a population of 10 million. Urbanization means that 4% of the rural population moves to cities each year, while 1% of the urban population moves to rural areas. Find the long-term proportion of the population living in rural areas. This is a steady state problem. Let's set up the transition matrix. Let state 1 be rural and state 2 be urban. 4% of rural moves to urban, so PRSYU is 0.04. 1% of urban moves to rural, so PU-TISH-R is 0.01. The remaining proportions are PR-R equals 0.96 and PU-0.9. We are looking for the steady state vector S, which satisfies T times S equals S. Let S equal AB. From the first row, we get 0.04a equals 0.01b, which simplifies to b equals 4a. Since the proportions must sum to 1, a plus b equals 1. Substituting, we find a equals 0.2 and b equals 0.8. The steady state vector is 0.2, 0.8. This means in the long term, 20% of the population will live in rural areas. Question 3. This one involves a Leslie matrix. A population of a species is modeled with 2 age groups, juveniles and adults. The fertility rate for juveniles is 0, and for adults is 4. The survival rate for juveniles to become adults is 0.4. The survival rate for adults is 0.3. The initial population is 200 juveniles and 100 adults. Find the population after one time step. First, we construct the Leslie matrix L. The top row has fertility rates: 0 for juveniles, 4 for adults. The bottom row has survival rates: 0.4 for juveniles becoming adults, and 0 for survival of adults, as per the standard Leslie matrix structure. The problem states that the survival of adults is 0.3. This suggests a slight modification to the standard Leslie matrix formula. A more appropriate matrix in this context for a two-stage Leslie matrix would be L equals F1 and F2, S1, S2, where S2 is the survival rate of the adults who stay in the same age category. Based on the notes, it seems the intended matrix for this type of problem is L equals F1, F2, and S1, S2. So we get L equals 0, 4, 0.4, 0.3. We are given the initial population matrix S sub 0 equals 200, 100. To find the population after one step, we calculate L times S sub 0. Performing the matrix multiplication gives us 400, 110. So after one time step, there will be 400 juveniles and 110 adults. The population has grown. Question 4. A factory has two machines, A and B, that produce light bulbs. 85% of bulbs from machine A work. 90% of bulbs from machine B work. The factory receives an order for 200 bulbs, and it uses machine A 60% of the time. What is the expected number of faulty bulbs in the order? This is a conditional probability problem, not a Markov chain, but we can still use a tree diagram and matrix-like thinking. First, let's find the probability that a bulb is faulty. The probability it comes from A and is faulty is 0.6 times 0.15. The probability it comes from B and is faulty is 0.4 times 0.10. The overall probability of a faulty bulb is the sum of these, which is 0.13. That's a 13% chance of any given bulb being faulty. For an order of 200 bulbs, the expected number of faulty bulbs is the total number multiplied by this probability, which is 26. And finally, question 5, a more advanced steady-state problem. A taxi driver services 3 taxi ranks, A, B, and C. The probabilities of returning to each rank after dropping off a customer are given in the transition matrix T. Find the steady-state proportions for the time spent at each rank. Again, we are looking for the steady-state vector S, which satisfies T times S equals S. Let the steady state be S equals A, B, C. We set up the matrix equation. This gives us a system of 3 equations. We only need 2 of them, along with the fact that a plus B plus C must equal 1. Taking the first row equation gives 0.5a, 0.7b plus 0.2c equals 0. Taking the second row equation gives 0.2a, 0.6b plus 0.2c equals 0. If we subtract the second equation from the first, we get 0.7a plus 0.9b equals 0, which tells us that 7a equals 9b. We also know a plus b plus c equals 1. From the first equation, we can also see that if we plug in b equals 7a 9, then c must equal 4a 9. Substituting all of this into a plus b plus c equals 1, we get 20a divided by 9 equals 1. This means a equals 920, or 0.45. Then b equals 7/9 of 920, which is 720, or 0.3, and c equals 4/9 of 920, which is 420, or 0.20. The steady-state proportions are 45% at rank A, 35% at rank B, and 20% at rank C. This means in the long run, the driver will spend 45% of their time at rank A, making it the most used rank. We have now solved 5 IB-style problems, covering the key skills of constructing and interpreting transition and Leslie matrices, predicting future states, and finding steady states. This completes our review of Markov chains.